Okay, I'm going to talk briefly here about the squeeze theorem. It's kind of a creative way to find a limit if we're kind of out of other options. Okay, and this one also I think is pretty intuitive. It might be hard to come up with the origination process of how to find the functions you can use to squeeze. Okay, I think the idea is pretty straightforward. So let's take a look, and then we can talk later about how much I'll make you use this one. So here we have f is less than g. Then what do you think's going on here? That is the limit. The limit of f is always less than or equal to the limit of g. If f is less than or equal to g when x is near a, except possibly at a, and the limits of f of g both exist as x approaches a, then their limits have to follow suit. Okay, well, that's pretty kind of straightforward. Let's see where this is taking us. So let's bring in a third function. F is less than g is less than h, less than or equal to. When x is near a, except possibly at a, then k. Here's the big part. Here's the big deal. The smaller function, which is f, that's the guy on the bottom. The limit there as x approaches a, if that's equal to the bigger function, right, which should be on top. So if I drew a picture of this, here's your picture. So f is on the bottom, right? F is always less than or equal to. H is always greater than or equal to, and g was in between. So the squeeze theorem simply states that if f as x approaches a has a limit that's equal to h as x approaches a, and g is always in between, then it gets squeezed to the same limit point. Okay, that's the squeeze theorem. So if okay, I hope that's not confusing. I switched up my h, f, and g. In this case, h is the smallest, f is in the middle, and g is the biggest. All right, so if h is less than or equal to f is less than or equal to g, an open interval containing c, then as the limit as x approaches c of the little function equals some limit is equal to the limit of g as x approaches c, which is the bigger function, and f is in between, then it gets squeezed in. Okay, and what I can do, so let's take a look at this one, for example, sine x over x. Okay, and we'll take a look at the squeeze theorem, and then I'll ask you to know these two special limits. Okay, the limit of sine x over x as x approaches 0 equals 1, and the limit of 1 minus cosine x over x as x approaches 0 equals 0. Of course, we couldn't use our direct substitution method there, right, because we don't have any way to sub in. You just be divided by 0, and then there's nothing much we can do. We could use our numerical approach for both of these. We could use our graphical approach, and now we can use the squeeze theorem. So let me show you what this would look like. First, I have to find two functions to squeeze it in. So that's where I'd give you some help. Okay, so I know that I'll have my cosine function. Cosine of 0 is 1, and cosine function looks like this. I'm going to pick another function, an easy one. So you should all know what function this is. That's let's use the notation from the slide before. The bigger function is g, the little function's h. So this would be g. That's the constant function 1. This would be h, my cosine function. Okay, and I'm kind of skipping some steps here because I don't want to spend a whole lot of time on this squeeze theorem. We won't really use it that much. We'd have to kind of figure out sine x over x looks something like that. Okay, it actually kind of does something like this. It gets, as x gets bigger, sine oscillates, so it just gets smaller pretty quick as x goes to infinity and to negative infinity. It does something like that. Okay, So the hard part of the squeeze theorem is coming up with this, which is what I'm giving you. I know sine x over x is less than 1 and is greater than the cosine function over a certain interval, right? So I know that this to be I know this to be true. I'm on pen. Sine x for this particular function, let me jump to my better writing tool here, maybe. So I know that over some small interval that this is going on. It's really the sine x over x is less than 1, and the sine x over x is greater than cosine x. And my interval could be, call it what you want. That's going to be, we'll just say, doesn't really matter what values I choose as long as it's true. Okay, so between negative pi over 4 and pi over 4, this is a true statement. Okay, so how do I use the squeeze theorem? Well, I need to know what the limit, and we're interested in what happens as x goes to 0, right? I want to know the limit as x goes to 0 of this function, right? So the idea is if you believe me that this is true, and again, I kind of gave you this piece. Otherwise, we'd have to think of a creative way to make that a true statement. But if this is true, if you believe me what's in red is true, then you can tell me pretty easily the limit as x goes to 0 of 1. That's one of my properties. That's a constant. It's always going to be 1. And the limit of the cosine function as x goes to 0 is equal to what? Well, we have 3 ways to do this now. We can do the numerical approach, get really close to 0, see where cosine's going. Graphical approach, look at the graph. Or now we can do the direct substitution. Remember, if the cosine's a nice function at x equals 0, I can just plug in 0. It's the same as the output, right? So because the greater function has a limit of 1, and the smaller function has a limit of 1, and our function is squeezed in between them, then therefore by the squeeze theorem we can say that the limit of sine x over x as x goes to 0 is 1. Okay. All right. Now for our last approach here. Okay, I'm going to call this this is our real, so find limits we can go numerical. We can go graphical. And these are kind of the non-mathematical approaches. And now we do the mathematical approach, analytical. Okay, and we have a couple of these already where you can just do plug it in or direct substitution if you can. We can't do that for this one, right? Because if I plug it in, I don't get a value. I'm dividing by 0. We have the squeeze, which we won't really use that much. And now I'm going to give you a couple other options. And the first one is, I'll call divide out technique. Okay, so I can explain this kind of based on what I'll give you the theorem after I do it, but I can also explain this kind of in what we know from rational functions, right? Because we know that about that hole in the graphs. We can kind of use our knowledge, prerequisite knowledge, to get this. Let's see if this makes sense. First of all, probably haven't done difference of cubes in a while. So if I wanted to factor the difference of cubes, you might remember it's cube root, first cube root squared, second cube root squared, that's 1 squared, which is 1. And then the product of the 2 cube roots, 1 times x. And then the signs, this sign never matches that sign, and this guy should always be positive. Okay, so be careful here. You're going to be tempted to do this, right, and cancel those out. But really, that's not the same function. So imagine we cancel those out. Then you're just looking at this quadratic function. But the reason they're not the same officially is because this quadratic function has domain all real numbers. right? This rational function has domain all real numbers except x equals 1, and that's the point we're interested in. But if you remember what's happening when x equals 1, there should be a hole in the graph, right? That's not an asymptote. So when there's a hole in the graph, we have a limit there, right? So that means that I can find the limit by plugging it into this piece. What would happen if we canceled it out, right? Because this function, the factored guy, the whole thing, is the same as this function, just the quadratic piece, everywhere except at x equals 1, right? If you plug in 5, they cancel out. If you plug in -10, they cancel out. The only difference is that x equals 1. The rational function doesn't exist when x equals 1, but the leftover piece, the quadratic, does. Okay, so this is what's called the dividing out technique. These limits are the same. Okay, so we have to be careful. Let's see. What I circle in green, that function, is the same as this function, is not the same function as what I'm going to circle in red. They're not the same function. However, they have the same limit at the point we're interested in, which is at x equals 1, because we know there's a hole there. So what would the limit be? Well, this is the same steps you did when you found the y value of the hole. You plug in the x value to what's left over, to your function, as if you did cancel these out. So that's 1 squared plus 1 plus 1. So the limit is 3, right? And like I said, these are the ones we're going to be doing. The more interesting functions where you can't do direct sub. We won't really do a lot of, we'll use numerical graphical approach to check our work, or to, if we run out of other options. And then we're going to plug it in after we do something else, like in this case, divide out. Okay, so let me show you the graphical representation of that. If you were to graph this thing, it doesn't look like a rational function. Most rational functions have asymptotes, right? This one doesn't, because we talked about that. It's just you end up with the quadratic after you factor. And what happens is there's just one hole in the graph, right? So the idea here is officially is f is what we're given, and we're working with g. They're almost the same function, except when x equals 1. So the theorem's going to follow like this. So, okay, here's your strategy. Do direct sub if you can. If you can't, we're going to try to do something like, here's the official wording of what we just did. We're going to be given f. It's going to be the same as g, and then we can do direct sub, okay? When the limit of x approaches c cannot be evaluated by a direct sub, try to find a function g that agrees with f for everything except the point we're interested in. Okay, so that's what we just did. We were given f, we found g. F and g are the same everywhere except at the point we're interested in, x equals 1, but it doesn't matter, they have the same limit. Okay, so that's just a lengthy way to say, do some algebra and then do direct sub. Okay, so here's another example. Dividing out technique. And not the same function, but I'm allowed to do that because it's the same limit. X minus 2, and then I can do direct sub. Okay. Almost, I got one more method, one more special method. I'll save it for the next video, and it'll just be a short one.